Okay, here we apply an input voltage which is of this kind, which is alternating voltage, alternating input signals. Now once they pass through this transformer, then if it is a step down transformer, then this voltage is not 220 now, it will be lesser, it will be smaller. If we use a step up transformer, then this voltage which is 220 volt is now here will be bigger than this 220 volt, but I am using a step down transformer, so the voltage will be lesser than this value. Now once this reached here, suppose the positive half cycle of this voltage. For that I will plot another figure. Okay, it will be better if I use another figure. So here we have the same circuit diagram. So there is nothing different. Here we have the P1 terminal and this is the P2 terminal of primary coil of the transformer, and here we have the S1 and this is S2. Here we have the P1 and P2 terminal of the primary coil of the transformer, and here we have the output signal which is of alternating current. Now let's suppose the positive half cycle of this output signal, this one, passes through this transformer. Once it's reached to the secondary coil, then this P1 become positive and P2 become negative. Here we have a resistance, okay, we call it a resistor here. We also connect a resistor here. Why we use this resistor here? Because we, for the calculation of output voltage, let's suppose we had given a current here. For the calculation of output voltage according to Ohm's law, V is equal to IR, we need a resistor. So the current will pass through this load resistor, and we will use a connector voltmeter here to count the voltage drop here, which is V0 here. Now this side become positive and this side become negative. So if it is positive, this is the P region of the diode and this is the N region. So if it is positive, it means that the P region of the diode is connected to the positive terminal. And this is the N region and this is negative. So it means that N region of this diode is connected to the negative terminal. So this diode is in forward bias mode. It's on. So current will flow through this diode and the direction of current is from positive to negative. So the current flows in this way. This is the current, input current, output current, yes. The current which is flowing after through the device. Now next we consider another, I will draw another figure here. The same figure but with different polarity. This is S1, this is S2, this is P1 and this is P2. And this is my output signal. And here we have, this is the P region and this is the N region. Now positive half cycle, for positive half cycle, this diode become forward bias and we have a current in the output source, output resistor, output source. Now let's suppose that the negative half cycle, this was the positive half cycle. Now next we have the negative half cycle. So let's suppose this negative half cycle reached to this secondary coil. Then once negative half cycle reach, then this will become negative and this will become positive. Now if this is negative, then this negative terminal is connected to the P region. If this is positive, which is connected to the N region. So the P region, P sides of the diode is connected to negative terminal, and N side of N region of the diode is connected to the positive region, positive terminal. So the diode is now reverse bias, in a reverse bias mode. It's off. So there is no current flowing through the circuit. So the positive half cycle crosses the diodes, and we have on the output source we have the positive cycle, while the negative half cycle were blocked by this diode. So there is no output source. So it means that if this is my, let's suppose I'm driving it here, if this is my input signal, so this is my input voltage, let's suppose input voltage, and this is the maximum value of voltage Vm, and this is omega t. This Vi will be equal to Vm sine omega t. Now the output voltage will be of this type. This is my V out. Now this is the positive half cycle, this is the negative half cycle, this is the positive half cycle, this is the negative half cycle. Now once positive half cycle reach here, this diode become forward bias, so there is a current in the output source. So there is a voltage drop here. If we measure the voltage will be like this. It's of this nature. Now next we have the negative half cycle. When negative half cycle reach to this secondary coil, then this diode become reverse bias. So the current is not flowing through the circuit. So the negative half cycle were blocked by this diode. So there is no, this diode is not allowing the negative half cycle to pass through this circuit. And then we have positive cycle again, then we have this situation again. Once this positive half cycle reach, then this become positive, this become negative, this diode become forward bias, so there is a flow of current through this diode, so there is a voltage drop V0, which we can measure by using the voltmeter. And so again the voltage will be of this type. And then we have again the negative half cycle. Once negative half cycle reach here, then again we have this situation. So the diode is become reverse bias, so it's blocked the negative half cycle, so there is no current. So this rectifier basically allows the positive half cycle and block the negative half cycle. That's why we call it half wave rectifier, because half portion of the input signal is allowed to pass through the diode, through the circuit, while negative half cycle is blocked by this diode. So there is no current and no voltage drop across this load resistance. This is the load resistance. Normally we represent it by RA. This is RA. So this is one situation. But we know that, so this is my omega t, and this is the maximum voltage Vm. But we know that there is a 0.3 volt or 0.7 volt barrier for germanium, and this is for silicon. Like the barrier height is 0.3 volt or 0.7 volt for germanium or for silicon respectively. So it means that initially if we increase the voltage and the value of voltage is less than 0.3 volt or 0.7 volt, then there will be no current. But once the input voltage become greater than this 0.7 or 0.3 volt, then there will be a flow of current. So it means that initially, if we are, this is for the ideal case, but in reality, like in general or in practical life, if this is the positive, negative, then initially for 0.7 volt, like up to 0.3 volt or 0.7 volt, there is no current flowing through, or there is no voltage drop across the output source. So after 0.7, then if the input source is a value which is greater than 0.3 volt or 0.7 volt, then we have a flow of current. So here we have a situation like this. So it moves, increases and then decreases again, and once it reaches to 0.7, then again there is no flow of current. So the output source looks like this. So here we have no current because this is negative half cycle. So again here we have a 0.3 volt is lost by overcoming the barrier height. So 0.3 volt will be absent here. So the output voltage will be lesser than 0.3 volt or 0.7 volt than the input voltage. So this is for the practical case. This is all about what we call it, all about full wave rectifier. In the next videos, the videos which I already uploaded on my YouTube channel, those videos contain all the details about half wave rectifier, because we have different parameters of half wave rectifier which we will calculate it. Like we have to calculate the root mean square value of the half wave rectifier, the average current, the average voltage, and we have the ripple factor, we have the efficiency, and we have the peak and burst voltage. All these quantities which I already discussed in my video, which I already uploaded in my YouTube channel. So I will share those videos also with you people. So hope you understand this half wave rectifier. And also there is a full wave rectifier. I have already uploaded the full wave rectifier videos on my YouTube channel. So I will share the link of those videos, and you will see the difference between half wave rectifier and full wave rectifier. So this is the whole idea. So it's allow only the half cycle and block the positive half cycle and block the negative half cycle. It's allow the positive half cycle and block the negative half cycle. Now, one thing more. Why it is DC current? Because for DC current we need a shape like this. That DC current will be constant. The current will have a constant value. But here, if you look at here, this current is not constant. It's unidirectional because we have all the positive cycle are here, because it's unidirectional, and current flowing in this way, So it's a unidirectional current now. But there is a variation in the output signal. So it means that this current is not a pure DC current. It contains both AC component and DC component. DC component because it's a unidirectional and the current is flowing through this direction, always from this terminal to this terminal. So it's a unidirectional because this current is unidirectional. But DC current should be constant. So here it is not constant because it contains the AC component of the current. It contains both AC and DC component. This contains both AC and DC component. We call it pulsating current. Now to convert this current to this one, we use another device here. Or somewhere in the flow of this current, in the flow of this current, in the path of the flow of this current, which is called amplifier, which we will discuss later. How to convert this pulsating current, which is unidirectional, and it also contains the AC component, into this pure direct current. We use another device which is called amplifier, which we will discuss later in a more detail. Thank you. Hope you understand this topic.